Swayam Prabha. Digital India. Educated India.
So when we talk about, you look at those three green boxes, what three words which we really worry about when we talk about concrete structures? Do we worry about workability of concrete? I can see where that yes is coming from. Students don't worry, teachers don't worry, field people worry about it. Because it's important. I mean, otherwise you won't get the money if you don't place the concrete. Okay, then what is the second one? What is that for? Design for? We told something, no? Two types of design. Design for commissioning. Structure has to stand, so it needs to have that strength. Okay. Now, what is durability? It's essentially strength of the system for long time. Okay. Designed for commissioning, but now designed for durability means that whatever you have on day one, that property has to sustain for the, what is design life and service life difference, or what is design life, what is service life? Code doesn't tell. That depends on the type of structure also. Okay, if you're talking about major bridges, may not be 50 years, maybe 100 years. Okay, but some of these are actually deemed to satisfy requirement based on the experience and other similar structure. We say they will somehow satisfy those requirements. Okay, so anyway, service life is basically you want that structure to be safe during that period. Okay, the structure has to be safe for itself, and also the users need to be safe. Okay, now how do we achieve this all three? By doing something to the concrete. No more the old OPC or cement, sand and water. That's not the concrete which we talk today. It's very, very different concrete. You are seen in the lab. If the chemical admixture dosage is slightly changed, SCC will not behave the way it is supposed to, right? So it is not simple. Okay, that story is gone. That anything you do with concrete, it will behave. It's not like that. Okay, so the SCC, which is supposed to move without any additional force, will sometimes require a lot of force to move. We have seen that in the lab and other. So especially if it is not, if you take more time to place the concrete, the slump of that SCC or the fluidity will significantly decrease, and it will not move, and you will need lot more energy to to place it. So how do you measure workability? So what is it indicating is when you say something is more workable, if you want to relate that, what is that word which you would use? Flow. So you need energy. Okay, so it's essentially a matter of like how much energy you require to place the concrete where it needs to be. For example, a concrete which is workable for a slab may not be workable for a column or a shear wall. Same concrete. Because what is the difference? Slab, you just place and push it, it will level it, right? But if it's a vertical element, it needs to flow down and compact. That is much more difficult to do rather than doing the same thing on a slab. So the same concrete which is workable in one case may not be workable in the other case, and vice versa. So it's all about how much energy you require to place that concrete. Okay, if you want to count in one word, it is the energy required. Okay, so how do we achieve that? We can put mineral admixtures, we can put chemical admixtures, not just by adding more water. We should not do that. Okay. And what is the third one? Top right. Good particle packing. And what do I need to pack more? You like to pack it with more cement or more aggregate? So you have to have well graded aggregate, not only coarse aggregate, well graded, very fine aggregate to coarse aggregate. Okay, we also sometimes use fine inert powder. Okay, limestone powder, for example, is used abroad. In India we don't use it much, but so particle size, so that the small particles will fill the air voids instead of cement going and filling the air void. Okay, we don't want cement to fill the air void. Minimize the amount of cement used. Cement should not be used as a filler, but you will use a little bit so that you can have a medium to carry the remaining thing. You will need to float these other aggregates, no? Okay, you need to float these other larger particles, so you need a fine powder slurry to carry them. Okay, so that's what we say cohesion, cohesive mix. We want everything to be together. You don't want the mix to be segregating, or aggregate different, sand different, water different, cement paste, that you don't want. So you want it to be very well, you need to have well graded aggregate so that you can achieve those. Okay, so that's about workability. To the top 3 rows which you see, those materials in right proportion, we can get enough workability, strength. But if you want really durability, you need to also cure the material very well. Otherwise, it will be like on paper, you will have every material, but it will not really show what you really want. And why I am saying this is, it is not that for strength you don't need curing, but strength is not very sensitive to curing. In other words, if you do not cure a concrete, let's say, not really the way you want it, it may still show adequate strength, but not durability. Okay, why? Because strength you usually measure on a cylinder which is taken from the from inside the concrete, right? And when you talk about durability, you are talking about the peripheral concrete. This is one thing which I liked in the site where we visited. They have precast shell, right? Second site. That means the cover concrete is quite good. Now you do inside whatever you want, I don't worry much. That's one good thing about that approach. Because the proper cover is maintained, the quantity, because it's precast, probably they will also cure that very well. So the cover concrete is very good in that case. Okay, the site which we visited in the afternoon. Okay, so essentially, if you put the right materials in right proportion, see, there are 1,000 types of concrete. A lot of different concrete mixes are available, but all made out of 3-4 materials only. So proportion matters a lot. Okay, this we discussed a little bit, right? I think we discussed, no? Yes. Yes or no? You're not sure. Okay, now you can see that on the right side, I think that we did not discuss at that time. Okay, so that minimum quantity of fly ash, so that you actually see the benefit of fly ash, is at least 25%. If you do not put that much, you don't really, yeah, if you don't put that much, it will not really. I was thinking that the sign is reverse or not. Okay, so minimum 25%. If it is slag, minimum 40%. If you don't see this much, let's say if somebody is coming up with a mix with 10% fly ash, please don't call it fly ash concrete. It's not. Okay, it's too little a quantity to see the benefit of fly ash. Okay, now No, because see, that also will depend on the amount of water which you use, not only the powder material. So you have to see, what I mean to say is I can have a very high strength concrete with very high strength concrete, not high performance, high strength concrete with less fly ash. If you're thinking only about strength. But generally speaking, if you want high performance, which is essentially the durability parameter, strength is also a performance parameter. Okay. But so that's a difference. One is high strength concrete, other is high performance concrete. Where when you say high performance, which is subset of what? High performance is the superset and high strength is subset. Okay. So I can have a high performance, if I need high performance concrete, better to go with more and more fly ash or slag. If you put too much, maybe, and if you don't cure very well. Okay. Yeah. Because I don't have that, probably Manu might have talked about it, the pozzolanic materials, right? The pozzolanic reaction is very, very important, for which you need to have calcium hydroxide from the OPC system that has to react, and then you will get more CSH in the same volume. So if you put too much of fly ash, then I mean there are systems where high volume fly ash with 90% and all that is there, but then you need to properly cure. A lot of additional effort is required to achieve the real behavior. Okay, for all practical purposes, I would say go with somewhere in this, the second box on the right side. If you follow, you will really get good quality concrete. That is the one step. Then the next step. Yeah, the fly ash or slag. That is the cementitious content we are talking about. Yeah, in the code they say cementitious, right? So that is essentially these kind of ACMs. Okay, now the advantage of this, you remember that the service life chart which we showed, where time versus the damage level. Do you remember any of you? Okay, so there, if you look back into that slide, can you open that slide in the hostel or here? You have it? The service life chart. Yeah, so there you can see an arrow, the rate by which. So the initiation time depends on two things. One is how much chloride you need. The other is the time taken for chloride to penetrate through the concrete cover. So you can see here the blue one is the OPC concrete, red is the fly ash. See on your printout, if you can't see things in color, you may want to use your pen and write. Later on you won't understand otherwise. And the black, let us forget about that for this lecture, but it is also a very, very good quality cement which is still in research state. Okay, LC3. Okay. Now you can see the slope. Now go through, let's say at 5 mm depth. Okay, which concrete has more chloride in the first graph? Which one has more chloride in the 5 mm depth? OPC. That means what? Speed of penetration is more or less? More. 10 mm, same thing, right? If you look in 10 mm, in the case of PPC, you don't have even very, very small amount of chloride has reached 10 mm depth. Okay, this is a graph obtained from a laboratory study where we put different type of cylinders, we put it in chloride solution. After 35 days, we took it out and then made this chloride profile. How much chloride has penetrated into the concrete? Okay, very clearly OPC is performing very good or bad? Bad way. Now see the graph on the right side. Black is the diffusion coefficient for OPC. It's much higher than that for fly ash, and I think the color is reversed over there, right? Yeah, this black is not same as that black. So you, anyway, text is written, so it's clear. Okay, So what does it mean? Should we use OPC or not? If you want durability, let's stop using this pure OPC business. Okay. Now, one more thing. These tests are based on 28 days strength. Okay, whatever 28 days, how the concrete behaves or how much hydration has happened, that is what the tests were done at very short time, 28 days. But this our fly ash and slag, they continue to hydrate for longer time. Okay. Now you can see here on the y-axis you have resistivity. On the x-axis you have time. Okay. Now this is essentially, what does it show? Service. So the resistivity is increasing for the green, orange, or whatever, red color, all that, right? Fly ash, slag, and calcine clay cement, limestone system, and the gray one over there is the OPC. Very clearly, it is very, the rate is very less. The gray one, the slope is much smaller than the other one. What does it mean? When you talk about fly ash or slag systems, over a period of time, you can really have high strength and better durability parameters. It may not show up, or it may not show that good properties in 28 days. What it means is, when you cook sambar, you have to wait until the dish is done before you taste and rate it. I don't know. Did I connect to you? You understood? Before the dish is fully cooked, you cannot taste it and then say it is bad. You have to wait. Two examples I can tell where, one is a bridge project, other is a metro project, where people actually, like after 6 months, they realize that it is so good at concrete, and that made them to use fly ash and slag. In one case slag, in other case fly ash. Because it's recording, I can't tell that. That's I don't like the record. Okay. So in one case, what happened is they were so hesitant in using slag, and we cast some cubes, kept it on the site. After 6 months, we said, now let us do the test. After 6 months, they got ready. The strength was good enough, which was actually not showing very high early. It was actually M40 type design, and it came to like 60 or 70, something like that, in 6 months. Then everybody was happy. Okay, now no problem, go for slag. But it took 6 months for them to convince. Okay. Now in another case, what happened is the test failed in resistivity. No, RCPT, it failed. One sample it failed, and then they were going for demolition of the structure. And it's actually a slab on grade, means on ground. It's not going to collapse. Nobody's going to get killed and all that. So then we said, okay, why don't we just take a core? This is about after 7 months. We just take a core and then do testing on it. We test and everything is passed. So this 28-day magic figure, you should not blindly go by that. You should see what is the structure for, and take bold step in approving the designs or concrete. Sometimes we say, okay, code says this, so I will not change it. Code is not Bible. I mean, we need to actually think, like apply your engineering mind and then see, make your own judgment. As an engineer, we should also make our own judgments and then see if it is okay or not. So even though that the second case I'm telling, the concrete did not meet the contract requirements on 28 days, but before the structure is actually put in use, the concrete has reached the properties required. So is there anything wrong in approving? Think and tell me. So it's, I know, see where the answer no came from, because it's all about money. It's all about money. We also have to respect that part. You can't, nobody is there to do business for charity. right? So we cannot just say, go demolish everything. You have to assess whether it is safe, unsafe, what is the safety level, if then, decide on how to do and what to do. Now on the right, so same thing, migration coefficient is another, you will see that when we go to the lab, all these testing setups. So a point to make is 28 day is not something which you will have to blindly believe and then make decisions. Okay, if you make gheer, payasam, right, it takes time, or gajar ka halwa, does it take time to cook? Can you make it in 10 minutes? Maybe someday some company will come up with it, but still it will not have that particular taste which you get when you take 4 or 5 hours to make carrot halwa. You know what I'm saying? Have anybody tried to make this? Do you know how long it takes? Still not in 10 minutes. You can't get that, right? You need long time to cook. So same way, fly ash, slag, etc. If you wait for longer days, you will get better properties. Okay. So there are also efforts to see 28 day strength. Can I actually, if my in-service load is going to come after 1 year, why should I worry about 28 day? Right? Because when you apply the load, that doesn't know what is the number of days of casting, from casting and all that. So on that day, at the time of load application, whether the concrete structure will have enough capacity or not, that is the question one need to answer. You can do something like warm water curing. So that's what, see, what we are saying here is like, if in 100 days, so you can look at here 100 days what will be the property, and in 28 days what will be the property. You can even actually relate. So effort is going on to actually say equivalent. If you use this material, instead of 28 days, you consider 120-day result. That the gray one is OPC. There are graphs. I don't have it here, but there are. Yeah, if you just in my other course material, it's already there. You will see very clearly, like at 28 day, there will be a convergence, and then you will see that it, for the, how do I show that? I don't see anything on the screen. Okay, so in case of OPC, you'll have the graph will go something like this, right? In case of fly ash or slag, the graph will keep going like this. The flattening part will take more time for fly ash and slag. Okay. Now I'm going to show you an example where, because these are all the actual numbers which we got by through experiments in the lab, and we can use these numbers for doing to real example. If you have a project, if you want to show somebody something, you can use these numbers, okay, to get you approximate values. It's not like if I'm saying the steel is going to corrode in 98 years and 5 months and 6 hours, no. Okay, but at least you will know it's 90 plus. So that is enough to make decisions. If somebody is saying like, okay, the material combination A takes 90 years, the other one is 89 years, I will probably go with the second one, right? If it is L1, if it is less costly, I'll go with that. So techno-commercial aspects, both you have to look at, not only technical and not only commercial. Only technical we go when we don't worry about money. Okay, most of the time we have to worry about money. So here you can see cover depth is one parameter, diffusion coefficient, which is speed by which chlorides penetrate. For different type of concretes, you can see different numbers. And then boundary condition, which is chloride threshold, how much chloride you need for the steel to start corroding. So based on this, we estimated service life for 3 different cases. You can see OPC, 3 different mixed designs. Now what does this say? See the black and red, it's almost parallel, no? But if you look at a vertical line where it crossed the zero line, or sorry, the 0.5, 50% probability, which is the mean value, there is a significant difference, at least 10 years gap. But point here is whether OPC is better or equivalent to fly ash and other cements. What do you see? In this case, see, when we first draw this graph, I was also surprised and I was thinking like, is it something wrong which I'm doing? Like it's showing like in 10 years you will have corrosion. But then there are many cases where we see corrosion in 10 years. So OPC, for God's sake, after this course, if you can avoid OPC, please do. You might say 100, contractual agreement, this thing, that thing, and all that. But if you really want to build durable structures, please avoid 100% OPC. Especially if there are people from water-related structures. You really need, very compact concrete so that water doesn't get in. So you need to have, I think, fly ash or slag, those kind of systems. And the more you wait, it's going to become more and more compact. Microstructure will be more compact. Permeability will be much, much less. Okay. Yeah, you are asking something. Sulfate resistant. Yeah. So what is sulfate resistant cement? What do we change in that cement? No, if you add slag, definitely all these fly ash, slag, etc., they really improve sulfate resistance. Okay, but if you buy sulfate resistant cement, this is essentially a cement with less C3A. Okay, because A is what reacts with sulfate. So I will not give enough reactant, so my reaction is curtailed there itself. Okay, that's the idea. Anyway, so anything which is more compact is good. Okay, so here very clear, this is far apart. Blue is way, much far away than the other two. Forget the, the black one for today's class discussion. At least look at the red and blue, or fly ash and OPC. Okay, now how do we bring it into the practice? If you say software, there are softwares available. Okay, that is also possible, but sometimes it's also good, like in your reinforced concrete design classes, you would have used design charts. So here you can see, I'll just go show you how this graph can be used. Okay, you start from top left. That's where we start from, and we end up at E1, E2, those A1, A2, B1, B2, C1, C2, D1, D2, E1, E2. Okay, you see those points? That's clockwise direction. We will move starting from A1, A2. So in a structural design office, the first step is to decide the cover depth. Who will design? Who will decide? The structural designer will decide that. Okay, cover depth. And that A1, A2, 0.2, what is that? That is the acceptable probability of failure in 100 years. Means when I reach 100th year, what is the probability of corrosion initiation? And I am assuming that to be 0.2. If I say what is the probability of corrosion initiation today, what you would assume? 0, right? You don't want any corrosion today. Okay, so you go from 0.2. So you pick one of those lines for various cover, and then go to the right. You pick cement. Okay, now once you pick cement, I think I'm doing bad. Soham, you will already learned all this. Okay, so cement, which one? So you pick based on the type of cement mix which you have, you pick one of the lines. Then you go down. So until there, mixed design is done in the office. So mixed design is there in paper. Now, who really decides what will be the chloride diffusion coefficient and all that? Who has the biggest role? The person at site. Okay. So if that person puts more water or less water or mess up on the mixture proportion, then you are in trouble. So you go from cover depth to the type of cement or binder to be used, then the concrete. Now let's say you go to C1 and go down, where you are going to decide what is the type of concrete you want to use. Not cover depth is decided in the office, binder is decided in the office. Now on the field you want to decide what will be the type of concrete. Now D1, you see the third line we have picked, because when you draw horizontal line it hits around 100. E1 is around 100. Okay. Now if I say I want to determine this diffusion coefficient for every truck of concrete which comes, it's not going to be practical. This is one of the challenge with every durability test. It takes time. So people, what they do, they tend to test durability property of the concrete in the lab. But actually there is no quality control measure. Like slump, is it a quality control parameter? Slump, quality control. What does that mean? What is the meaning of quality control parameter? So every concrete batch which comes to the site or every concrete truck, what is the first thing you do? You do the slump test. Why do you do slump test? To control the quality. So quality control test is something which you can easily do on site. And if the slump is not passing, you send it back. Okay. So the supplier of concrete will ensure that it meets the slump requirement. Okay. So compressive strength, is it a quality control parameter? Yes, but not really. You cannot really control that on the site, but very often we do this compressive strength test. Okay. And if it is not meeting for a particular, let's say you cast a column and you made a cube out of the same concrete and it tested the cube, and if it is not meeting, then you will say that column is not good. You will have to go back and test the strength on the column. So it's essentially a quality control, but which still takes some time. So similarly, there is also another parameter which is resistivity. We already know about resistivity. So we are bringing this resistivity also along with the compressive strength. Compressive strength is for mechanical properties. This resistivity can be for the durability property. Okay, so you can relate. So here on the bottom left, you see three curves. That is for relating the diffusion coefficient DCl to the resistivity of the concrete. Higher the diffusion coefficient, resistivity is lower. So we are saying let's go for a mx dy. That's the idea we are talking about. Mechanical mx, durability dy. Okay. Now similar graphs are there for other cases based on. Now this is not there in your slide printed, I think. So there is also software available, Life 365. You can write it down. Free software. You can actually play with different type of mixers, and then this will give you what is the. It's not very complicated, very easy to play with. You can select different type of material. All this can be, in the software. You can just tell what is my mix design, and it will pick its own values. And if you want to put your own, user defined parameters, that's also possible. Okay. And that will also give you probabilistic curves showing what will be the time to corrosion initiation, etc. Okay. Now, among these three parameters, like we talked about this, all these four parameters here. surface chloride, chloride diffusion coefficient, chloride threshold, and cover depth. So here you can see 3 of them. Which is most sensitive? Based on this graph, which one do you think is most sensitive? You read the x-axis and read the y-axis and then tell. It's not there in the printout. I think. Is it there? Yeah. So maybe I want you to draw this. Draw it on the paper, on your wherever you are. This is the fixed second law of diffusion, which you see in that yellow box, which is used for predicting service life. Which one is most sensitive over there? DCl, which is diffusion coefficient, X, which is cover depth, and chloride threshold, because it is very steep. Okay, so you see that the intersection point is 0, and what it's essentially telling is, if I change the percentage of that particular, let's say I pick only the X curve, okay, I change that by 10 units. What is the change in Y? Can we say something like this? So it has changed this much. This much it has changed for a very small change in X value. Is this clear? I don't want to just keep moving if it's not clear. Is it clear? A small change in the parameter is creating a big change in the time to corrosion initiation. That means the steeper the curve at 0, it's going to be more influential or more sensitive. So that's again telling cover depth is very critical when you want a durable life. Okay, the most critical thing is cover depth. So at site, if you really want, if somebody cannot change your mix design and all that, forget it. At least do the cover depth business properly. Okay, then diffusion coefficient. After that, only chloride threshold will come. So cover depth is the most important. Okay. So the mx dy thing. So this again you will see in the lab. So I'm not going to spend more time. This is a practice with, like, every concrete cube which you test for compressive strength. We actually also test weight of the concrete cube, right? Why do we check weight? Just to see if somebody has put enough aggregate or not, if the proportion is right or not. Okay, that will be very less. Percentage voids will be very, very less. Main idea is whether the mix is uniform or not. For example, let's say you made concrete cube and actually the concrete was segregating. Assume a case, and you made a cube. From where you pick it depends where did you scoop the concrete from, right? If the aggregates are settling in the wheelbarrow, which concrete do you use for making cubes? Let me ask. For come out of the lab, okay? Which concrete at site? What you will do? Truck will come. It will drop the concrete into the wheelbarrow. Am I correct? Then what do? Is it the first wheelbarrow or the second one, or what do you do? Which one you use for making cubes? Yeah, because it depends on how well you mix in the truck also. Okay. Idea is you should use the concrete mix which is very well mixed or homogeneous in nature. If it is not done properly, it will show up in the weight. Imagine you have more aggregate and less cement, or if you have more cement and less aggregate in that particular scoop which you took, that will show up in the weight. That is why we are always testing the weight of the concrete cube, so that we ensure that it is homogeneous mix. Okay, and now same cube can we also test resistivity. This takes only a minute or two to do this test. Just put the instrument on the cube and then take the reading. Done. Okay, very simple test to do. Now, I think I have another slide to show this thing on the sports complex where we visited. So here we said, we put it in the contract document, we put that the resistivity should be 30 kilo ohm centimeter square, kilo ohm centimeter. Okay, the first row over there. Now there is a catch here. If you say only surface electrical resistivity, people will take measurement on the dry concrete. Cube, it's okay, because when you do the compression test, it's coming like a wet cube is coming, so it's fine. But if you want to use this for measurement on the actual structural element, okay, you have to ensure that it is wet. Otherwise, if it is dry, you will get very high resistivity value. So it may be wise to say wet resistivity, wet surface resistivity, rather than just saying surface resistivity. Okay, laboratory testing is very different than field testing. What we are talking here is field testing. My next presentation, I'll show you that. I'll talk more detail about this particular slide. Who will measure saturation level? That's why SSD. Yeah, so we go then another slide. It's not written here, but SSD is what we are recommending. Okay, which is the case for compressive stress. Now in the site, you have to really worry about it. How do we achieve that wet condition? So we are saying, like, spray water and keep it wet for 30 minutes or so. That also depends. If it's depending on type of concrete. If it's very impermeable concrete, 30 minutes may not be enough. If it's porous concrete, 30 minutes is enough. So there are a lot of things. So it's not very simple, but we have to define the condition. No, like measurement on dry concrete will not help. You will get very high value, but that's not what we really. When does corrosion happen? When the concrete is wet or when the concrete is dry? Who said dry? When the concrete is wet or when the concrete is dry? Wet and dry. I'm talking about the moisture condition at the steel surface. Dry or wet? You need moisture, right? In the reactant, which in the cathodic reaction on the one of the reactant is, you need moisture, right? So if it is very dry, you will not have to worry about corrosion. So when you talk about all these quality control, all these things, what we need is, I want very high resistivity when the concrete is wet, not when the concrete is dry. So that's what I want to ensure by doing the testing. So wet resistivity is more important than the dry resistivity. So this is one of the project where this kind of approach was implemented. The outer two spans were M40 concrete. The middle span was also designed as M40 concrete, but it took that 6 months time. I told earlier about some 6 month time, and when we did the compression test again, it was passed. This is that. Okay. So in that time period, 6 months, we were able to convince, and we were able to implement this M40 D30 concrete. Okay, and this is, I think, 70% slag, resistivity value of 30. Yeah. Okay. So I think we have to start with, and to publicize this kind of approach, we can say 30 blanket number. Don't ask more questions here and there. Now here, one more thing I want to show, forgot to talk. See this blue line on the bottom left, OPC curve, where is it stopping? Somewhere around 23 something, 23, 24, right? We could not get, let's say 25, we could not get more resistivity in the OPC concrete. That's why the curve is stopped there. But the other two, very, very high resistivity is possible. this one. The blue one, there's only one point which is about 20. That curve is some of the data is from this plot. This is like 5-6 year old data, but the curve is recent one. Okay. Anyway, we have very good evidence that this is how we should do things. Now here again you can see M40 design. The blue green one is M40 D30 design. Okay. So look carefully on the mixed design, OPC1 and OPC2. I'm going through very detailed so that you won't forget this thing. Okay. OPC1, OPC2. How much is the cement content? People from field, have you seen mixes like this? Nowadays, we see a lot of mixes with very high cement content. Sorry, I have this animation and it's going back and forth. See, when they were doing this thing, I said, we are not going to allow anything. In the beginning, I said, try with 390 is okay, but not 400. Okay. But then we insisted, but still at least we could do this with the 409. That's, you see the PSC mix, 410, we can say. So it is doable. That's what I'm telling. And I'm not talking about a classroom project. This real bridge, on this bridge, the cement used was 410 PSC. So you have to actually use the admixture technology well. Okay. Most cases we are not using it. You have to do mixed design properly. PSC is Portland slag cement. 70% slag. This mix, the one on the right side is 70% slag. Yeah, it's a pre-blended mix. So 70% of that, see, if it is either PPC or PSC, if it's pre-blended, the company will try to maximize the amount of slag or fly ash. Okay. So it's point what I'm trying to make is that you don't need 600 kg cement, you don't need 500 kg cement, 400 is enough. The trick is to have the aggregates gradation properly and use adequate chemical admixtures. That's where the trick is. And that you have to do it at the site with your kind of aggregates, your kind of cement, your kind of admixtures, compatibility between cement and admixtures, all that have to be looked at. Okay. Is it clear? Now, then we also did the testing on site, because usually people say, okay, this is our laboratory study, site is different. We did actually testing on site. This is a proof. Okay. So actually I wanted to test these slab panels for 2-3 years. But unfortunately, the minister came and they dumped this thing into the ocean. This panel, because they wanted to clear up the site. Literally, they dumped it into the ocean. Okay, big loss, I would say. Anyway, so here you can see what is the service life difference with OPC and PSC. How much times? Time. 4 times. So I really wonder why we don't use. You can get better strength, you can get better durability, but still we go by pure vegetarian restaurant. Pure OPC. So please use this data wherever you want. The paper is published on this last week. It's available online, or I can mesh. It's available now. Yeah. So it's available online. Full details of this project is there, because people always say, where is the field data? To actually, if you go back to your company and then say, They'll say it's class lab. No, it's not lab. It's actually a major bridge project. Okay. Now, other thing which we need to worry is the cover. We saw that in the previous slide, the most sensitive parameter is cover depth. Okay. This very clearly shows you put about 10 millimeter more cover, your service life increases easily by twice. Okay. So in this equation here, this equation over here, X is the cover depth, and that's the most sensitive parameter. So if I increase, but I cannot keep on increasing cover, you know why? Because it will start cracking. I don't want to do that, but at least I should provide what is allowed. So I think you should start doing something like, you know, penalize people if the cover is not adequately provided. And usually there is a resistance on measuring cover after the formwork is removed. Do we measure cover depth? Unless there is a problem, we don't. Why? You don't want to know. It's better sometimes not to know the problems. Okay. Now I have directly experienced, that is why I'm telling. The projects where we say go measure cover depth, people will do all sorts of things not to measure. The reason is in the IS 456, it is given if the cover is not this much, you can actually, there is very strict guideline given on that what should be the cover depth. If you say 40 mm cover plus minus 5, I think it's allowed. So if it is beyond that, then you are in trouble. Once the data is collected, you have to take action on the data, right? So people don't try to collect data, but let me see if I have that slide here. Yeah. So my suggestion is go with this. Tell people that I'll come back and measure. In the contract document, you write. Then they will ensure everything is right. Okay. So go back. So this is a example from project in Chennai. About 6-7 years old building. The building does not exist today. 6-7 year old. Okay. 3 big apartment complex, big buildings. I think about 500 families were staying. It was demolished recently. Okay. So we, really very good investigation was done on this. You can see the column on the left side picture looks fine. This is how we usually see, right? Yes or no? Shirt is very good. What is shirt? Paint. Shirt is the paint. Okay. Then the middle one is when the paint and skin is removed. The mortar plaster is the skin. Cover concrete is the flesh around the bone. Steel is the bone. Shirt is the paint. Skin is your plaster. I'm not saying you need skin, but somewhat analogy is this is okay. And then you have flesh, okay, which is the concrete. Then you have steel, rebar, which is the bone. Now, what you see on the middle picture is when we removed that plaster and paint, it looks like this. What is the issue? Tell me. Where is thick plaster? Only on one side. The other side? So in all these columns, you have multiple snakes. What is a snake I'm talking about? No. Snake like this. Undulations on. One snake is the rebar. Okay. You put the formwork and then you put the rebar, it will try to lean here and then lean there and then lean here like that, right? So that is the first snake. Then what you do? You put the formwork. Now, before placing the concrete, you need to have the straight formwork, right? So what you will do? You will put a prop from right side. Then you figure out that actually I put more. Then you will put another one on this side. Not at this level, but on this side here. So this will push this way. And then there will be another one. It will push this way. So eventually have a formwork also, which is a second snake. You agree this? Formwork is not vertical, right? Typically. Then you place the concrete. So you take the formwork out after the concrete hardens. Then what happens? You see this curvy concrete surface. That is a mistake. It is supposed to be straight. You got a snake again. Now how do you fix it? Put the plaster. Cover up everything and then make it straight line. This is why we use plaster. Okay. Now you see the right side picture, 2 inches of plaster, this much. That means that column is shifted to the other side by 1 inch, because both sides should have same plaster thickness, right? Okay. Now, what you observe here is the bottom face, about 1 meter from the base of the column. You can see that marked region in the middle drawing. See, all these things, if you don't write or mark on your printout, it is not going to be clear for you later. Okay. You should write down. Maybe I should let you write before I go to the next slide. And please write on the printout, not on your other book. First day I told this. Now what you see there, you see so we opened at that region and we found that where is the corrosion? This is very common. That's why I'm going very slow in this. Okay. Where is the corrosion? On the bottom, about 1 meter. Any structure you go, you will see this problem. Most of the, I'm not saying any structure, most of the places nowadays you will see this problem. Very clear, idea, a very clear indication that concreting is not done properly, and that is kind of a shear wall what you see there, or a concrete column, thin element. Concrete is not placed, it is not compacted, so it is very porous, and every day you mop. That's a problem. So where does the water go? It capillary rise. So that column will get water every day, whether it is summer or winter. If you are mopping, that's going to get water. And it gets enough oxygen also, because it is not submerged case. So it's an ideal case for corrosion to happen. Believe it or not, this structure, it's in 7 years of its construction, it was demolished. Okay. All the jacketing is not a remedial measure. Jacketing is only a remedy for MX, not for the durability part. Only strength. Okay. So I don't want to mix. I'll talk to you later on that if you are interested, because I'm not talking about the repair practices here. Okay. So because you raise this point, jacketing will give only temporary mechanical strength. If there is corrosion happening, you have to first stop the corrosion from happening before doing any strengthening. One is electrochemical repair, other is strengthening or structural repair. One deals with the chemistry, other deals with the mechanics. You have to have both. Okay. So that plaster I showed, this picture, top left, this is again from another building. After 8 years, you see the plaster in that corner. This is a piece of a corner element, of a column element. Okay. You see the corner plaster. Then the right side is when we did the phenolphthalein test on it. What is the lesson learned? What do you observe from this? Plaster is of no use. Here that plaster is fully carbonated in 8 years, whereas the concrete is not carbonated. Okay. Same way, when you talk about chloride resistance, plaster has absolutely no role. When you talk about carbonation resistance, plaster has absolutely no role. Okay. So I don't know, is it clear that on the top right image what it shows? It's a fractured piece after 8 years of construction. When we did the phenolphthalein test, the plaster shows full carbonation, whereas the concrete shows absolutely perfect. Now the corrosion on this structure happened because of chloride. That's a different story, and this is just to show the carbonation part. Okay. So don't think that plaster is going to do any good. It's only going to help you cover up all the mistakes you have done. Okay. Huh? I didn't get it. Maybe, I don't know, but this particular photo which I'm showing, it's all OPC concrete. But that could be some special, maybe expansive admixture or something will be there if it is for water tank. Okay. Now many companies will have expansive products. They put something, especially if it's for water retaining structures, you don't want any crack, so you don't want shrinkage. So what you do is you put a little bit expansive material so that it expands and closes the crack from opening up. So for example, if you say amusement park or like your water retaining structures, go with a little bit of expansive agent. It will help you. It will help you to seal. It actually put a pre-stress on the concrete. That's what it does. So you can't, it won't pre-stress by expansion, not by pulling the strands. Okay. So this is from the same structure where we found corrosion starts within a year. What is the time? Corrosion starts within a year, and this photo on the top left, it's taken around 5-6 years. Do you expect this to happen in structures? So this is our problem, and you can see that admixed chloride, which is the chloride from the water. We discussed this earlier also. Okay, chloride from the groundwater. So please enforce testing of groundwater. Okay. Now this is another one. This is from our own campus. Architects give this nice design pergola, but engineers, we are failing in constructing it properly. So you have to, this will be like 60 mm thick. Okay, 60 mm thick, and then 1 or 2 meters, whatever, depending on the design, at least 1 meter high, and then you have to place this. So these are all where we can actually go with precast. You make these small panel elements and then just stack it there, but that work you can do on ground. See, the advantage of precast is everything you can do on ground except the connections. Now when you do things on ground, the knowledgeable engineers can actually check. See, we can't expect the labor or construction worker to check every cover. They don't know. You can't blame them, and they get less salary than engineers. So you are supposed to be checking that. You take more money from the company, so you are supposed to build better. Take more responsibility also. So here again, this is just very, people on campus, they can recognize which building it is. One of the hostels. Okay, so you can see the cover. Just around 5 years. Anybody staying in this hostel? Okay. When you go there, you see how the cracking is happening on that. Okay. This one again, you have most of the time you will have these leakages. We don't care much about pipelines. We try to put pipelines and then don't allow them to move. First lecture also I told about this. You have to provide a rubber gasket or leave some air gap around the pipe. The hole which you will drill for the pipeline to go through, make it bigger than the OD of the pipe. Give enough space so that it's easy for the workers. Like usually you will see in all these shoot for pipelines, it will be so congested that you can't really even stand there and work. So these, at the time when you get the design drawings, you should say, no, I cannot, I need more space there. And when they start leaking, and nowadays we have this practice of covering up everything. APP membranes are available, you just put everywhere, close everything. I don't want to know the problem until it is too late. So that is something which I would recommend. As much as possible, keep the concrete element exposed. As much as possible. Don't put a cover on top of the concrete again. It is not required. It adds budget, like money, you will need more money for that. And it doesn't give any protection, rather it creates negative issue. Why? Because it will hold the humidity inside. It will not allow it to dry. Even if somehow water gets in there, it will hold it there. Okay. Now on campus here, we are now slowly getting rid of these things. False ceiling. What it is doing is sometimes the inside of this, like a space between the false ceiling and the roof, the humidity will be very high. Okay. And I don't know if you know this, there is a hook which holds these frames, okay, or the channel. It's like a topaz blade, no, very thin blade element, and they corrode very fast. There are many places where we see that this falls. Either you provide a very good hook, the S clamp I'm talking, either you provide at least very thick S clamp, or better is remove this. There is no need of false ceiling, unless there is a special aesthetic. But the aesthetics is how you change your feelings, something which you like other person may not like. So maybe we can have some nice painting on the roof itself. At least I will know what is going on in the roof. Yes. Acoustics. You can put something like that over there. I don't want an airspace in between, which is going to keep it very humid. That is my challenge. Okay. Now cover block, the other day, Justin, you have it? Okay. Yeah, so you can see here, there are cases where plastic cover blocks, now it is not widely used, but it is still there in the market. Please don't use plastic cover block. Okay, why? Any comment? Think. See, plastic does not bond with the concrete. Now you are providing a plastic cover block. I have my bar is here. My steel bar is this. My hand is the plastic cover block. Now what will happen? Water will, or more oxygen, air, everything will have a direct highway available to the steel bar. Okay. Now this side of the concrete on this side will shrink this way. Concrete on this side will shrink that. So you will have very good crack for all the deleterious elements to reach the steel. Now you have a fine, it is like cracked concrete, if you remember, very small anode, very large cathode case. So in the long run, it is not very good. So what we are recommending now, and also this second one, it looks very good, but look is not what we really are looking at. Now Umesh actually found that these cover blocks, about 1 to 2 mm, all the surface, entire surface of the cover block 1 to 2 mm is already carbonated by the time you put it in concrete. Maybe you can share that image in the WhatsApp group. Like very clearly we can see the cover block. So actually the block was carbonated before he used it for making specimens. Okay, so this is something which we need to look at. Make sure that the cover block is also very good against carbonation and chloride resistance, because you are actually creating a direct path towards the steel. So that has to be very good quality. Again, when you place these blocks, which is the second case, it can rotate. When you put the needle vibrator, it will move from left to right. All sorts of movement will be there. It's very difficult to hold it in one place. So we are recommending to go with this circular shape with a hole where you will put the cover block like you see on the picture on the right side, where it is on the stirrups. Which one need the real cover? Stirrup, if you are given an option, only one cover block available, either for stirrup or for the what bar? What bar? No main bar. Okay. For the longitudinal bar or the transverse or shear stirrups, because that's the one which really needs, which has less cover, so need more protection. Okay. If you're talking, there's no main bar. I don't know what is main bar. Huh? Forget code. Forget code. I'm seriously saying it's recording, but this is not right. You can't get rid of that main. Huh? Huh? You got to change the practice. Okay, and tell all your friends, both are main. My shear check is also as important as flexure check. Okay, you will not pass a drawing or a design if the shear check is not passing, right? So why the other one only is main? Okay, we got to change this. Okay, so yeah, what you were saying? Okay, see, in the drawing, what is your purpose? Purpose is to ensure that the steel, whether it is longitudinal or lateral, gets adequate cover, right? For that, for ensuring that, you as an engineer can do anything you want. It will only increase. Actually, a good designer will tell cover required for the stirrups. The stirrups. Yeah. I think it says nearest reinforcement, not now you are changing my vocabulary. Not longitudinal. I said not. I think it says nearest rebar. That's what it says. Nearest. Okay. So for horizontal elements, or if the rebar mat we are talking about, then you can go with these kind of blocks. No issue. You don't need circular cover disc for that. So the title says cover block or cover disc. Okay. We usually use only cover block. So can we change another vocabulary? One more, add another vocabulary, cover disc. Okay. Now I remember the one more concept. When you want to test, let's say you want to test durability parameter or something on concrete structure. If you want to test compressive strength, you will need a core. Okay. What will be the typical cover depth? Typical cover depth 30 or 40 mm. That will not be sufficient to do a strength test. You need deeper or longer cylinder. So you go behind the bar, like you core more. But if you want to test durability parameter, you don't need that much. You only need cover disc and not a core. Okay, disc from the cover region is enough, not a core. Now I'll tell you the story how we came up with this. One of my students was looking for to test the carbonation depth in Chennai Metro. columns. Over a year he struggled, but nobody was giving permission because they don't want to take a core. Then they themselves gave the idea, don't ask for core, ask for disc. Because in the structural design, whatever is outside my stirrups, I don't consider. So you can take a disc element and not a core element. And that is enough for our all durability studies, because we want to see how much is the chloride penetration or how much is the carbonation depth, which will not be more than the cover depth. Okay, but again, another thing is, if the structure is in bad shape, if a doctor says I want to test bone marrow, you have to give it. Right? You cannot say I'll only give blood and not the bone marrow. So it depends on the case. Now, how do we actually handle cover depth issue on site? In the contract document, if we can say that I will come and measure the cover depth after the formwork removal, before the plastering. After the formwork removal, before the plastering, you measure. And there are equipment available which you can use just to scan. Cover meters are everywhere. You can say, okay, I'll measure like 100 points at random I will take depending on the structure. And then based on number of points which pass, all that you can figure it out. Let's say you can say if 10% is, sorry, if 90% cases are passing, it's okay. If it's 80% is passing, means if you measure 100 cover point cover depth measurements, if 80 of them pass the requirement, then you say penalty is 10%, money, more financial. Okay, if it's 90% passing, this much. If it's 60% passing, this much. So you can put these kind of conditions in the contract. If you do this condition write this condition in the contract, the contractor will ensure that it is met. It's only a matter of putting a watchdog. All these things which we talk, if it comes in the contract document, things will happen. So where is the problem? Problem is in writing the contract document. That cut and paste business is something which we have to really work on. Okay, contract document. So after the tea break, I'll show some documents which we have prepared. Okay, so yeah, yesterday we saw the shell. Not yesterday, Saturday we saw precast shell. This is the best thing about that. You have a very good quality cover concrete. Even if you mess up at the site, it's only the hardcrete which gets messed up, but the cover concrete will be very good in that case. All those in BG Shirke's project, everything outer concrete is very good. And they also provide proper cover because it's all mechanized. You don't have to really worry about it. So this, you can employ a person who will ensure compaction, cover and curing. 3 things. Penalize it is not met, incentivize it is all met. Okay, in which we can. Now other concept is a birth certificate for concrete. When babies are born, before you go out, they will give you something, right? What is the test which they do? Blood test. Which group will write it on that? So, and whatever other tests are there. So this essentially you're certifying that there is no abnormalities and all that, right? Now here, can we also do similar way? One for mechanical properties, a set of parameters for the durability properties, and then we can say if you have all these things, then your structure is good to go. But how many places we actually practice this? This is nothing new. It's not, if you look in FIB document, it's there. Birth certificate, you Google it. There. But we need to bring it into our construction. Now we did for the sports complex, we actually did it. I'll show in the next, it's not called birth certificate, but we did it for that structure. So mechanics is important, chemistry is also equally important. You are asking something. Okay. Okay. Rest of the things you read, and summary, I think next